All right, here we go. So chapter 5, part 3 is the lesson for today, and it's about solving trigonometric equations. And you think about solving, for algebraic functions, if you think about their graph, their shape is either a line or a curve, and the curve can be pretty complicated, but it's never periodic. And by that, I mean it never goes back around and around and around the way it did in previous values in the domain. So there's one aspect of solving trigonometric equations that will be new, and that is the periodic nature of the trig function. So if there's one solution, you see how there must be infinite. So we're going to be describing those infinite solutions in terms of the period of the function. So that's a little bit new, but it's pretty straightforward once you see it. We're going to solve them using algebraic techniques, and we're going to apply some identities. So the first one is this, example 1. 5 times the cosine of x equals 3 cosine x plus the square root of 3. And hopefully after Friday, you guys have become accustomed to seeing trigonometric functions treated like an algebraic entity. In other words, like x or y or z. So we can subtract it from both sides, add it to both sides, divide, multiply. All the rules of equality apply. Commutativity, associativity, etc., etc. So everything you've been doing to solve algebraic equations up to this point still holds. So Rachel, tell me what I should do to both sides here to get a solution.
Make them the same.
Well,
Or have them the same.
I want now that was for verifying identities. So, but for solving equations, I want to isolate the trigonometric term first, and then we'll use either a trig inverse or some other trick to figure out what x is. So that answer would have been exactly right on Friday when we're verifying identities. Here we're not doing that, we're solving it. So tell me what I can do to isolate the trig term here. Well, we do have the same trig term here, but think about this like an algebraic entity. If this were this equation, what would you do to both sides?
Put the x on one side.
So what operation would facilitate that? Good. So what should I subtract? 3 cosine x. Very good. So if I subtract 3 cosine x from each side, I get 2 cosine x equals the square root of 3. Everybody with me so far? All right. Now, what should I do, Colby? Divide by 2. Excellent. And so that gives me cosine x equals radical 3 over 2. And so x is going to equal the cosine inverse of radical 3 over 2. We could find that with a calculator, but it's right on the unit circle. And remember, this is the cosine is the x coordinate, so that would be right here. Make sure you have that unit circle memorized well enough to do what I just did. If you have not, then you're not ready for any assessments in chapter 4 or chapter 5, but especially chapter 5. Questions? Okay, so I know the x coordinate of the unit circle is square root of 3 over 2 right here, and that base angle is 30 degrees or pi over 6. So x equals pi over 6. That's a solution. How many solutions are possible? Infinite. So if I want a solution, this is perfectly valid. If I want every solution, then I would have to do an additional step. Now later on, they're going to ask us for every possible solution, and I'll show you what I mean by that. questions about this one? All right. So now you're going to see something that I haven't been able to do up to this point. I want you guys to work this one on your own. Once you get a solution, I want you to compare with other folks at your table. Make sure you guys agree. Rowdy, you'll have to turn around and compare with Jess and Colleen.
We're going to do two of them. You have those two. One is going to have white.
Well, that's how we're doing it. The x and the y or the cosine are positive. So we're looking for a solution in another. And also define the sine inverse. Sine inverse.
If you have, I think you should get that. This becomes just like your written subtract this one. So what does that mean?
This is correct. So find the point on the new circle. Let's write it down. Okay, so Colin, tell me what you got here. X equals what?
3 pi over 4.
So that's one way to say it, but typically when we talk about the sine inverse, we use a negative. So what you said was correct, but negative pi over 4 is also a solution. So excellent job. And the reason why, because you're going to get sine of x equals negative radical 2 over 2. And that has a solution both in Q3 and Q4. So the solution is 225 degrees or 315 degrees. But sine inverse is only defined in Q4. You remember that? I showed you we had to cut part of it off to make it a function. So the part we cut off was included the Q3 solution. So only the Q4 solution is possible by the inverse function. However, so this is a solution. Do you see how 225 degrees would also be a solution? So if we were going to list every solution to this, we would have to include that one as well. So, but we're not quite there yet. We're just finding a single solution using the inverse function. So this meets that criteria. Okay, so let's talk about tangent squared x minus 4. 3 times tangent squared x minus 4 equals negative 3. All right, so algebra. Clay, tell me what to do to each side first.
I would add 4 to both sides.
Excellent. So I get 3 tangent squared x equals 1. What should I do next, Jesse?
Divide by 3.
Excellent. So I've got tangent squared x equals 1/3. Now I'm going to apply the square root property. So remember, it's plus or minus. And the square goes away, of course, when I apply this. So if I, so I don't know if you remember this property of roots. So that allows me to write this as because the square root of 1 is 1, and the square root of 3 is radical 3. And then if I rationalize radical 3 over 3. So we have to consider both of those. We want a solution to both of those. Pretty soon they're going to ask us for every solution on the unit circle, but right now, just one will suffice. So let's see here. Tangent inverse of positive square root of 3 over 3 is that. We want to go into degree mode. Remember I told you radian mode's not going to make a whole lot of sense. 30 degrees, so that's pi over 6. And then if I do the same thing, but make it negative 30 degrees. So pi over 6 and negative pi over 6. So those are a couple solutions. There are more, even on the unit circle, because you know the period is pi for this. So if I add pi to both of these, I'll get 2 more solutions on the unit circle. And I can add pi over and over and over again, and I'm going to keep landing on a solution because of the periodic nature of the tangent. So it's going to make this true over and over and over again. Periodic functions will have infinite solutions. But here is a single solution which meets the brief of this problem. Okay, I think we're good on those. So let's talk about all solutions. So different scenario now. All solutions on the unit circle. So all solutions on the unit circle. New task. And I've got 2 sine x cosine x equals radical 3 sine x. So a big problem for us is when we have more than one trig function. We don't like that. We like dealing with one and only one trig function. So there's a couple ways I can go about it. Let's see what the most efficient way is here. Oh, okay, just factorization. Yeah, okay, so each term has a sign. Gotcha. Okay, so 2 sine x cosine x minus radical 3 sine x. So what I've done here is just subtracted this from each side to arrive here. Now to solve by factoring, I need to get one side equal to 0. You guys know that. Now I'm going to factor out the sine of x. So what I've done here is created a situation where I can apply the zero product property, which tells me if a times b is 0, then a equals 0, or b equals 0. So the zero product property allowed me to create these 2 equations where we don't have the problem of mismatched trig functions. So where is the sign of 0 on the unit circle? Here's where you have to know the unit circle. And I haven't been able to teach that as vigorously as I usually do. Usually I quiz mercilessly on it until the entire class has it memorized. But you guys haven't had the benefit of that. So think about the unit circle. What angles have a y coordinate of 0? There are 2. On the unit circle, what angles have a y coordinate of 0? I'll wait while you guys think about that. Say again? That's one of the two. 0. So 90 has an x coordinate of 0, but the y coordinate is 0 at 0 and 180. Good job, Clay and Rachel. So we'll write this in radians just because it's what's typically done in these type of problems. So this one tells me x equals 0 or pi, which is another way to say 0 degrees and 180 degrees. And we're only concerned about solutions between 0 and 2 pi. So over here, I've got cosine x equals radical 3 over 2. So there are two places again on the unit circle where this is true. And you can confine yourselves to the quadrants that have a positive x, which is Q4 and Q1. So what are the x values that cause us to have cosine x of radical 3 over 2? Macy.
1/2 and yeah, 1/2.
So we're looking for a radian solution.
Oh, sorry.
What radians give us square root of 3 over 2? So that would be square root of 3 over 2 for the y, but we're looking for it for the x coordinate. That's one of the two. What's the other?
11 pi over 6.
Yes, or negative pi over 6. But we want to do this because, see how we have to go from 0 to 2 pi? We can't use a negative radian in this case, not and satisfy this condition. So these are the four solutions to this equation on the unit circle, which at this point is all we care about. So the first couple examples, we were looking for a solution. This one, we're looking for every solution on the unit circle. We will expand that even further as we go forward. We will eventually be making an infinite list. Questions about that? Okay. So here's one for you, and I'm going to give you a hint. Use a u sub. So let u equal sine x. Solve it like a quadratic. Plug sine of x back in. Give you guys about a minute to work on that one. Once you're finished, compare answers with the folks at your table. And
So this is what almost normal looks like.
almost normal. One small step towards normalcy. If you'll forgive me paraphrasing Neil Armstrong.
No, I'm glad everybody's back. I just kind of get a glimpse of what it looks like.
Yeah,
I've
we're
forgotten
happy.
what it looked like to have an almost full room.
Yeah, it's cool, man. It's almost like I'm a regular teacher again. Again, once you get a solution, compare with the folks at your table and see if you agree. The wisdom of the crowd. In Great Britain, there was an experiment conducted where they took a jar full of candies and asked people how many were in it. The answers ranged from 50,000 to a couple hundred. The correct answer was 5,000. But once they averaged the hundreds of people they had polled, the result of the average was 4,999.8. So as a group, humans tend to be very intelligent. It's the same reason ants can build bridges and create livestock pens for aphids and do some things that baffle us. The wisdom of the crowd.
The same reason we have toilet paper so
Yeah, well, individually, humans can be very stupid. But
You get the mob mentality, you get stupid.
sometimes, but in general, groups tend to be more intelligent than individuals. Let's see. Okay, so I'm gonna work through this and you compare your work to mine. You see where and if you went wrong. So the first step should have looked like this. And then we're gonna factor this. So you need to find two numbers, m and n, that add up to -1 and multiply together to be 2 times -1 or -2. So -2 and +1 meet that criteria. So we'll rewrite this as 2u squared and then -2u plus u minus 1 equals 0. Now we factor by parts here. So we factor out 2u and I get u minus 1. And then when two numbers are relatively prime, in other words, they share no factors, I can always factor out a 1. And so I get 2u plus 1 times u minus 1 equals 0. So 2u plus 1 equals 0 or u minus 1 equals 0. So u equals -1/2 or u equals 1. Now we're going to dump u and go back to sine of x. Rip. So where is sine of x -1/2 on the unit circle? In two solutions. Yeah, can you tell me that in radians? So you're giving me the other coordinate. Instead, I want 210 degrees in radians.
7 power 6.
Yeah, and make sure you have access to that information, Ian. So 7 pi over 6 is one of two solutions. Bristol, can you tell me what the other one is? Say again? Not quite. If your knowledge of the unit circle is poor at this point, that's okay. It's a weird year. We've had a lot of weird stuff going on, but you need to rectify that. And like yesterday. So let's try again. If you don't have the unit circle in front of you, this can be a challenge, but certainly with access to it, if you can't figure this out, you haven't paid much attention. So tell me where the y coordinate is -1/2 other than 7 pi over 6 on the unit circle, Jesse. So that would be negative square root of 2 over 2.
It'd be 3 pi.
So that would be negative radical 3 over 2 for the y coordinate. We're looking for -1/2, Jesse, in Q4 for the y. Where is the y coordinate? -1/2.
-1/2 or 1?
Yeah, we're dealing with this left side first. So at 4 pi over 3, because you've given me that answer a couple times, you may have your, that's here. The y coordinate, the x coordinate is indeed 1/2. So that can be confusing. But the y coordinate, which is what we're concerned about, doesn't match. It's negative radical 3 over 2. So look through Q4. Tell me where the y coordinate is -1/2.
I think you have it written down.
Okay.
Yeah, I'm looking down. I have 7 pi.
So, well,
Well, that's
Yeah.
very. 7 pi over 4 is 315.
So this is 11 pi over 6, yes. So if, the day I went over the unit circle, I did it pretty quickly. You guys had to write down a lot of stuff in a short period of time. You may have had a mistake, that's okay. But now is the time to correct it before we take an assessment with the wrong information. So 7 pi over 6 and 11 pi over 6. And again, we're confining ourselves to the unit circle. So we don't care about the other solutions if they exist. Which they do, but we don't care about them. Now, where is sine of x equal to 1? Hold it.
Sine of x equals 1, that's going to be at 0 pi.
No. So we're looking for the y coordinate is 1.
Right, 90 degrees.
Okay, or what is it in radians?
Or pi.
Good. So these are the solutions for x on the unit circle.
What do you pi over 6? I thought it was pi over 2.
Oh, I'm sorry. I don't even know why I wrote 6. Losing my mind. I guess I was a little frustrated and I let that make my brain not function. Okay, so anyway, 7 pi over 6, 11 pi over 6, pi over 2. Hold it.
How do you tell if you're finding the y or the x?
Okay, good question, and that's something some folks are confused about. On the unit circle, the x-coordinate is the cosine of that base angle. Always, no exceptions. There are no exceptions to this rule, and if you don't know this, burn it into your memory now. This is a fundamental idea in trigonometry. If you've gotten to this point without knowing this, congrats on being a great I guess, person that fakes it, but this is a fundamental idea. You should have learned this immediately when I introduced the unit circle. And y is going to be the sine of that base angle, theta. Always, no exceptions. So for every point on the unit circle, x is the cosine of the corresponding base angle theta to that ray that you're considering. Y is the sine of that base angle theta with regards to that ray that's being considered. I might turn the heat on. Okay, moving on. Good question, Colby. I'm glad you asked it because I'm sure other people were confused about that as well. All right, so let's do this one together real quick. So I'm going to let u equal tangent x. Actually, tangent squared x is what I have to let u equal to create a quadratic. So that becomes 2u squared minus u minus 15. So equals 0. When I change u to, or tangent squared x to u. Now I need to factor this, so I need two numbers, m and n, where they sum to -1, and their product is 2 times -15 or -30. So -6 and +5 meet our criteria. So I'll rewrite that middle term. Like so. And then I'm going to factor by parts here. Just solving quadratics. You've been doing this since you were in 8th grade, probably. 2u times u minus 3 plus 5 times u minus 3. And what you want when you're factoring is to get, when you're factoring where the a value is not 1, and you regroup the middle term and factor by parts. So when you use this technique, it should always be the case that you have a matching binomial term at this point. If you don't, you did something wrong. Because the whole point is, on this next step, that we can factor that out to get this. And so, the zero product property tells us this has to be true. And then if we plug in tangent squared of x, so tangent squared of x equals positive 3. And then here we've got u equals negative 5/2, so tangent squared of x equals negative 5/2. The intermediate step in both cases. So the tangent of x is plus or minus the square root of 3, and the tangent of x is plus or minus the square root of negative 5/2. Now I can disconsider this result. Who can tell me why? The negative under a root, which creates what? What happens when I have a negative value under an even indexed root? Imaginary solutions. So imaginary solutions are invalid. There are no imaginary numbers on the unit circle. So I cannot find a solution on the unit circle or even in the realm of real numbers for that matter. So because this is going to result in an imaginary, I can disconsider that part of the equation. Now over here, I do have to consider, so the tangent inverse, and we have to use that because you remember the tangent is not on the unit circle. So, I mean, you could go around and calculate every single value of tangent, and if you're really good at the unit circle, you probably could figure it out mentally. But in general, you will have to rely on the calculator a lot heavier. And remember that the tangent inverse is only defined in Q4 and Q1. But we're considering the entire from 0 to pi. So there are going to be some solutions here that do not meet that criteria. So not the whole unit circle, just the top half. But we can figure this out. So tangent inverse of negative square root of 3 is negative 60. And the tangent inverse of positive square root of 3 is 60. So negative 60 and 60. So if I were to think about the unit circle, here at 60 degrees, we have a solution. So that's perfectly fine. You know, we're only considering this part, 0 to pi. But negative 60, do you see how that's not going to work for us? Now, the period of the tangent is pi. So if I go pi units in any direction, because the tangent is periodic, I will find another solution. So if I go pi units, this is not a valid solution, but if I go pi units away, I will arrive at a second valid solution, which is here in Q2. So I've got 60 degrees and 120 degrees. Add 180 to negative 60. Do you see how that gets you to 120? So if I add pi, because the period of the tangent function is pi, I'll arrive at another solution. And this one does meet our criteria. So the two solutions between 0 and pi. So 4x is an element of 0 to pi, which is what we were told to consider. I've got pi over 3, which is 60 degrees, and 2 pi over 3, which is 120 degrees. And those are the only solutions that matter, because as Caitlin pointed out, the other side gives us imaginary result. We don't have those values on the unit circle, so that's like asking what a unicorn smells like. It just doesn't make sense. This is a bad question, so we disconsider it. Questions about this? Something's mysterious. You better ask me again, because we're rapidly approaching the Chapter 5 test, which will be the first test of the second 9 weeks, and important to establish, a good grade early. So chapter 6 traditionally is probably the easiest chapter. In fact, I've had cases, and I don't want to make you guys overconfident, but I do want to show you that there's a light at the end of the tunnel. I have had years where the average score on the chapter 6 test is around 100. So chapter 6 will generally offset a slightly bad grade on chapter 5, but still, you want to set yourself up for success, so do as good as you possibly can on this chapter 5 test coming up. We've got this one more section. I don't cover chapter 5, part 5 as a whole. I cover only one question from chapter 5, part 5. So we've got effectively this lesson, one more, Wednesday study guide, and then I'll release the test. Sorry.
Could you explain one more time why you had to subtract, like, or add 180 to get 120?
Sure.
To get a solution?
So the task that we were set by the problem is to solve between 0 and pi, which is 0 degrees to 180 degrees. So negative 60 degrees does not meet that criteria. So I had to find the corresponding solution to that point that was in our solution range, if such a point existed. And because the tangent has pi for its period, I had 180 degrees, and sure enough, I did land in our solution zone. So that was also a valid solution. Caitlin?
If the range expanded all the way to 2 pi, would you be able to do like the opposite of 160?
Yes. So we would have 4 solutions in that case.
Yeah.
If we were talking about solutions on the entire unit circle was Caitlin's question. If that were the case, there would be 4.
All right.
So that's a good observation. Other thoughts, comments? Cool. So let's talk about a real world example. So a lot of times I'll skip these because they're kind of long and they take a minute or two. But in this case, I don't, because test question, often missed about this very topic. Grab this paper. Trump says, I get it. Okay, so here's the setup. A projectile. So the laws of projectile motion are the consequence of the work of Newton, Sir Isaac Newton, who developed the calculus and the application of trigonometry in the analysis of projectile motion at the rate people learn it. So if you were to take a class in college, Newton developed this at the rate people usually learn it through the course of a class. An unprecedented genius was Sir Isaac Newton, rivaled perhaps only by Galileo, Leonardo da Vinci, and Albert Einstein. But anyway, a great mind. And he developed these formulas that we now use to analyze projectile motion. They're not complete. They're slightly inaccurate. But those inaccuracies don't manifest unless we get close to the speed of light, which guess what? Never happens. So we don't have to worry about it. So as far as we're concerned, Sir Isaac Newton's formulas are still valid. Only as you approach the speed of light, I don't know if you remember that problem from an earlier homework where we talked about what happens to the mass of a thing as it approaches the speed of light. Nothing for the longest time until you're at a very sizable fraction of the speed of light, and then your mass starts to increase as a consequence. And time itself slows down for you. Weird. But we're just talking about regular motion here, which is almost never going to be near the speed of light. So we just use Newton's formulas. So important information. A projectile is sent with an initial speed of 350 meters per second, pretty dang fast, about the speed of a bullet, and clears a fence 3,000 meters away. So that's going to be our D. The height of the fence is the same as the height of the initial height of the projectile, so we can just consider both of those values. If it's given by this formula, find the interval of possible launch angles to make this happen. So this is like an artillery question. So soldiers on the field, when they're firing an artillery weapon, use formulas just like this. In fact, this exact formula in some cases to calculate the angle of fire. So let's plug in 3,000 for D, and then we've got 350 squared sine of 2 theta divided by 9.8. Where does this 9.8 come from, Macy? It is part of the formula, but do you know what physical property that is a consequence of? What do you think, Kobe?
Gravity.
Yeah, it's gravity. So on Earth, gravity is 9.8 meters per second squared. Also 32 feet per second squared, if you prefer the imperial unit. Would this be the same on another planet? No. Be about 1.6 on the moon. It'd be somewhere around half this on Mars. On Jupiter, it'd be about 3 times this. Well, Jupiter has no surface, but imagine you could, float in the clouds of Jupiter. The force due to gravity would be about 3 times that. The sun's, oh my goodness. Well, that'd be difficult to calculate without some numbers in front of me. But we'll suffice to say it would be huge. The sun it's difficult to overestimate the size of the sun. It looks like a little ball in our sky, but it is so huge. Light is generated in the core of the sun, and it slowly migrates its way out to the outer part of the sun, and then is emitted, and that's the light we see. It takes 10,000 years for light to get from the core to the surface. So if that gives you an indication of just how long it is. Because light travels at the speed of light in a vacuum, but the speed of light is slowed down by the density of the sun. Okay, anyway, back to this. Let's solve this. Typical algebra here, so I'm going to multiply both sides by 9.8. And I'm going to divide both sides by 350 squared. And then I'm going to use the sine inverse. So 2 theta equals sine inverse of 9.8 times 3,000 divided by 350 squared. So let's see what that is. This is going to be a little misleading, and I'll tell you why in a second. Let's see. So sine inverse of numerator 9.8 times 3,000 divided by denominator 350 squared. So it tells me 13.8 degrees. So I have to think about some additional solutions. So that's one solution at about 13.8 degrees. Now, remember the sine inverse is only defined in quadrant 4 and quadrant 1. Here we have an additional solution in quadrant 2 that we must find by symmetry. So there's another place over here in Q2 where it's also going to be true, and it's going to be analogous to this one we found down here, we would find down here in Q4, but we can't use Q4 because we're not talking about negative angles. So anyway, we need to find the symmetric point in quadrant 2. So that's going to be 180 minus 13.8.
Wouldn't the 13.8 be 2 theta?
Yes, so but we're going to take care of that in just a second. But that's a good observation. 166.2 is the other. Now, and what Holden says makes a lot of sense, because if I set the barrel's angle to 166.2, do you see how I'm shooting almost directly behind myself? Oops. So we don't want to do that. But 2 theta is going to equal between 166.2 degrees and 13.8 degrees. So if I divide everything by 2 here, I'm going to get theta has to be between, and I'll rearrange those. Typically we do ascending, in other words, the least first. So we'll write it like that. And this is including this bound, because the bound is a solution. So 13.8 divided by 2 is 6.9 degrees. Don't forget that bit. And then 166.2 divided by 2 is 83.1 degrees. So anywhere in that range is going to accomplish our result. And that's the case. Now that's a huge range, right? It'd be hard to miss. You'd have to almost point at the ground to miss, or straight up in the sky. And the reason why is this is just a ludicrously high speed for a projectile. Think how fast a projectile would have to go to travel about 4 football fields in 1 second. That is a ludicrously high velocity vector, and so you get this very large range. That would be difficult to reproduce with an artillery shell, without an immense amount of gunpowder, or maybe a rail gun system or something like that.
So the solution just means anything not in between those two angles will not make those events.
Correct.
Okay.
Yeah. So anything from here, including, as your initial angle of fire, will clear that fence. Okay, questions about that? Again, often missed test question. And the reason why people miss it so often is this part, being able to find the corresponding angle in the quadrant that's not defined by the inverse. Doesn't really give a solution, does it? Okay, so rewrite by using a single trig function. Here we're going to apply some identities. So for the first time, a solution will elude us unless we use one of the identities we've been taught. And in this case, the Pythagorean identity. Okay, so sine squared x minus sine x plus 1 equals cosine squared x. What's the big challenge with this problem, Rowdy? What makes this one hard?
Cosine and sine.
Very good. Good observation. Cosine and sine together. And so we have to rewrite this in a way that includes only one of those two. It's a lot easier to get rid of the cosine. And if you think about the Pythagorean identity, you'll see why. See how easy it is to rewrite something squared as the other thing? So because you got a relation between those two squared values. So this term will be easy to rewrite as sine. And then we can solve it using the techniques we already know. So I know that sine squared x plus cosine squared x equals 1. That's the Pythagorean identity. And if I subtract sine squared x from each side, I get this. So do you see how I can replace cosine squared x with 1 minus sine squared x? So I have sine squared x minus sine x plus 1 equals 1 minus sine squared x. So there's a couple things I need to do here in order to solve this. First of all, subtract 1, which will cancel both of these 1's out. Then I need to add sine squared x to each side. Like trigonometric terms here, I can combine, and I get 2 sine squared x minus sine x, and I canceled out everything on this side, so it's 0. Now I'll factor. So if I factor out sine of x, I get this. So if you have a GCF, that should always be your first tactic. Factor away that GCF. So now the zero product property tells me sine of x equals 0, or 2 sine x minus 1 equals 0. So sine of x equals 0, and we're concerned about solutions on the unit circle. So the y coordinate is 0 only in 2 places on the unit circle. What are they?
Pi over 6.
Now we're talking about where the y is 0.
That was a 2 pi.
Well, 2 pi, but we're going to use 0 for that value. And then also where? Pi. 0 and pi. It's getting a lot better. You guys are starting to get a feel for it. So 2 pi is another way to say this. But the reason why I use 0 instead of 2 pi is only 0 is included here. 2 pi is not. So, but you were right in general, but in this regards to this specific problem, we want to use 0. And then over here, I've got sine of x is equal to 1/2. So where is the y coordinate positive 1/2 in on the unit circle?
Pi over 4.
So that'd be square root of 2 over 2. We're looking for 1 over 2.
Yeah, 1 over 2.
Mm-hmm.
Would be pi over 6.
That's one solution, pi over 6. Then there's another one in Q2. What is it, Ian? Or, yeah, Q2. Give you a hint up here.
Pi or it's equal.
No? Looking for the y coordinate is positive 1/2.
Would be 7.
That's negative 1/2. So you have the right absolute value, but positive 1/2 for the y.
Negative 7.
No, it's going to be 5 pi over 6. So here's what I want you to do, Ian, and everybody else that has an issue with their unit circle. When you go home today, look Wikipedia, unit circle, and make sure all your numbers are correct, okay? Because if it's wrong, you're never going to be able to solve these problems. Make sure your unit circle is right. So here are the answers on the unit circle. Now, as I told you, we are eventually going to extrapolate those solutions to all numbers. So yeah, I guess that's in the next section. Let me just show you what that would look like. If I were to solve this instead of this, let's find one for all values of x. So we'll do just one this way for all real numbers. One thing we need to know is the period of the sine or the cosine. Wow, dude. This is a fairly lengthy problem. Huh? Yeah, okay, so that's a pretty easy solution now. Yeah, there's a neat trick we're going to do here. So sine x minus cosine x equals 1. So if I square both sides, I'm going to get a minus b squared is a squared minus 2ab. With me so far? Plus b squared. And then 1 squared is 1. Although we do need to be conscious of something, because when we square both sides, we introduce the potential for an extraneous solution. So we're going to have to watch that at the end. Plug in our answers, in other words, and see if they work. So here's the thing. Sine squared x plus cosine squared x see how I can substitute 1 for those? So I get -2 sine x cosine x plus 1, because sine squared x plus cosine squared x becomes positive 1 equals 1. Stay with me, guys. If I subtract 1 from each side, I get -2 sine x cosine x equals 0. Divide both sides by -2, which is valid. And I'll get sine x times cosine x equals 0, which means by the zero product property, sine x equals 0 or cosine x equals 0. So we've discussed this ad nauseum, basically. Make sure your unit circle is right. Where is the y coordinate 0? Well, that's at 0 or pi. This is on the unit circle we're considering first. Then we're going to find every possible solution. Where is the cosine 0? That's at pi over 2 and 3 pi over 2. So if we plug these in, let's start with 0. Sine of 0 is 0 minus cosine of 0, which is 1. So -1 equals 1. False solution. Now let's try pi. Sine of pi is 0 minus cosine of pi, which is -1. So minus -1 equals 1. 1 equals 1. True. That's a valid solution. We're plugging these back in. Remember, we squared both sides. We introduced the possibility for an extraneous solution, so we got to check ourselves. Then pi over 2. So sine of pi over 2 is 1. Cosine of pi over 2 is 0. 1 minus 0 equals 1. 1 equals 1. True. So this one's true. And then 3 pi over 2. So sine of 3 pi over 2 is -1 minus cosine of 3 pi over 2 is 0. -1 minus 0 is -1. -1 equals 1. False. So pi and pi over 2 are our real solutions here. Now, once we have them, we need to extrapolate every possible solution as a consequence. So it's going to be this. X equals the valid solution plus the period times n, where n is an integer. And then also the other valid solution. So that's how you would find every solution in the universe. We'll do some more of this in the subsequent section, but we found a solution. We found all solutions on the unit circle or within one period. And then here we're finding every solution, period. Every one that exists. And pay attention to what the problem is asking for. Right.
I was going to say.
Sure. Okay, so here we go. Your task for tonight is to do page 331, 5, 6, 13, 14, 19, 20, 21. So as usual, a brief assignment to reinforce what you just learned. I hope you guys have a great day.
Are assignments going to stay the same, how we've been doing them?
I don't intend to